So this one I want to work for you is one of the examples. It's not a fundamental problem, but it's going to illustrate some ideas that are going to come up for us. Okay. So our piece of interest in this particular problem is this bar right here. All right, that bar with center of mass G. And what you need to realize is that G is not rotating, but it is moving along a circular path. And since it's moving along a circular path, then that really means that um, X and Y components are not well suited to treat a situation like this. Okay, so what we need is we need some a coordinate system that's better suited for this, and that turns out to be um, a cylindrical system. So we're going to be looking at normal and tangential components of everything as we do this. And when we look then at our equations, okay, this guy is the same, but over here, this is a normal. So we're saying that the sum of the normal forces is the mass times the centripetal acceleration. Okay, and we get another one of these plus or minus things, which so that means every time we got to think through it carefully. But the magnitude of the centripetal acceleration is omega squared r. So if we know the angular acceleration, then the angular velocity, then we'll get it. Similarly, there's a tangential equation. So the sum of the tangential forces is m times a tangential. We get another plus or minus thing is mr alpha, the angular acceleration. Okay. Okay, so let me get rid of all that stuff. We'll get into it here. That wasn't right. Okay. I'll just do I'll just erase that. I got rid of the whole thing. Oh, good Lord. Okay. So we begin like we always do, which is trying to think about what's happening with the forces. Now we know here I've got some, I'm going to call it some tension. Let's call that TA. And we got some tension over here. We'll call it TC this way. And then we've got the weight of the thing, which is down here like this. So there's our mg. Okay. Now, in terms of our coordinate system, which remember we are going to set it up where we've got normals this way and tangentials this way. The two tensions are already aligned with how we want to set this thing up. So we don't need to do anything special with those. But take a look at mg. You can see mg, we're going to have to split into components. So I'm going to need here a tangential component for mg, and I'm going to need a normal component for mg as well. Okay, and that normal component for mg will have to be negative. Okay, so how do we figure out what those normal components are? Well, it turns out it's not too hard. We've got a 30-degree angle in here, and so that means that actually this angle right here is also 30 degrees right in there. Okay. Now, what that does for us is that means that the normal component is going to go as mg cosine theta, where theta is 30. But it's got to be negative. And it means then that the tangential component of my weight is going to go as mg sine theta. Okay. All right, we're good to go. Let us proceed as we normally do. Okay. Okay, we need the normal components. So in the normal direction, we're going to have TA up. Boy, that's really tiny. Let me make it a little bit bigger for you. Okay, we're going to have TA up, TC up, and then we've got our normal component of the weight down, which is going to be mg cosine theta. Okay, now omega, this problem gives us, it says it's moving at 6 radians per second. Okay, and so we know what omega is. And the centripetal acceleration in this case matches how we've defined our normal component. And so we can just come in here and put omega m omega squared r. We don't have to fuss with trying to figure out if it's flipped or not. Okay. All right. So we got two unknowns in there, TA and TC. Okay. So let's go to our next equation. The tangential forces, the only tangential force is that tangential component of the weight. So we're looking here at mg sine theta, okay? And that has to be MAT or MR alpha. So let's see if we can figure out what the acceleration is on those things. So I'll go ahead and put MR alpha in here. But then we got to figure out, is it going to be positive or negative? So positive AT is this way. That corresponds to an alpha, which is like this, and that is negative. Okay, so we've got to choose negative when we move forward on our algebra over here. All right. Okay, so the m's are going to cancel just like that, and we get that alpha is equal to minus g sine theta over r. Okay, and r is going to be 0.5. It's just the length of one of those rods there. Okay. Oops. Okay. All right. So let's get to our third equation because we still don't have the two tension values worked out. All right. We got a TA and we got a TC. Now I don't know about you, but my gut feeling is that they're going to turn out to be equal. Okay, but we have to prove that. We can't just go on our gut. We got to prove it. And so we'll sum the moments around the center of mass. And so I'm going to have T. I need this vertical component there. And I'm going to need this vertical component there. All right, those are going to go both be T cosine 30. So I've got TA cosine 30, and that's going to be negative. And then I've got TC cosine 30, and that's going to be positive. Those are both equal to 0. Oh, look at that. Look at that. Look at that. Look at that. Those cosine terms are going to vanish, and I'm left with TA is equal to TC. Okay. So that worked out for us pretty well. And that sort of matched our instinct. It's always good. Look, that took like 60 seconds to verify our instinct. Okay. It's always good to do that. Now, if these distances here had not been symmetric. Oh, I forgot to put the 0.4 in there. Well, I knew where it was going anyway. So we really need a 0.4. Oops, a 0.4 in here and a 0.4 in there to turn that into a moment. Sorry, rookie mistake. But I knew they were going to come out as a wash. But if it wasn't 0.4 and 0.4, if it's 0.4 and 0.5 or 0.5 and 0.9 or whatever, then this relationship would have not been true. But it is true, so let's use it. All right. TA and TC means what we really are dealing with is two tensions, and that is M omega squared R plus mg cosine theta. And that makes a lot of sense because the tension values have to fight against gravity, plus they have to provide the centripetal force to keep the whole carriage moving along a circular path. Okay. If we work out what that tension value is, it's 1325. Okay. And you can kind of see, well, what if the carriage was moving faster? I mean, rotating faster, then the omega squared R term would be larger. We'd have to have more tension, that sort of thing. Okay. And so that could put some limits on kind of bolts we're going to use or pins to keep this thing going, that sort of thing. Okay.